In this video, I'll describe a new statistic called chi-square and show you how to use it to make inferences. Let's start with a research question. Are some birth months more common than others? To investigate this question, you survey 200 people and make a table of the data. Now, I'd like you to pause the video and try to identify the parameter and some hypotheses you could make about the parameter. At first, it seems like there should be 12 parameters. The percent of all births that would occur in January, which we can also write as pi sub jan, and the percent of all births that would occur in February, which we could write as pi sub feb, and so on, one for each month. In this scenario, the null hypothesis would reflect the idea that no birth months are more common than others. Now, this doesn't necessarily mean that these percentages should all be the same, because some months have more days than others. January has 31 days, and February usually has 28. So if births weren't more common in January, there should be 31 divided by 365, or 8.5% of all births in January, and 28 divided by 365, or 7.7% in February, and 8.5% in March, and so on. Now, how can we test all of these parts of the hypothesis simultaneously? In the past, we've been able to make a compound parameter by subtracting one from the other, but we have too many parameters to do that. Pause the video for a moment and see if you can come up with a way to combine all of these parameters into a single compound parameter. The solution is to create a new type of compound parameter and statistic, loosely based on the idea of total percent error. First, we'll start with the idea of percent error. Percent error is a measure of the difference between what you observed and what the null hypothesis would predict. To compute percent error, you take one of the values you observed and subtract the value you would expect to get if the null hypothesis were true, and then divide by the expected value. For example, in January, we observed 15 birthdays. If the null hypothesis was true, then 8.5% of all birthdays should be in January, so we'd expect 8.5% of 200, or 17 birthdays. So the percent error for January would be 15 minus 17 divided by 17, which is negative 0.1176. Now, you might be wondering why we need to divide by the expected value. Let's think about what would happen if instead of surveying 200 people, we had surveyed 2,000 people, and 168 of them had been born in January. Now, the null hypothesis would still be the same. We'd expect 8.5% of people to be born in January, and 8.5% of the 2,000 people is 170 people. And I'd like you to pause the video for a moment and think about which feels like a more significant difference: getting 15 January birthdays when you'd expect 17, or getting 168 when you'd expect 170. Even though there is a difference of 2 in both cases, that difference of 2 is larger when it's out of 17 than when it's out of 170. And in our computation, this corresponds to a smaller percent error. So that's why we divide by the expected value. When we're thinking about the amount of error, it doesn't really make sense to have negative values, so we want to make the percent error positive. Although there are multiple ways to do this, it turns out that squaring the numerator will have some important mathematical properties that will make all of our statistical computations work out. And when we do this, we're no longer technically computing percent error. So I'll put this in quotes for now. So we can compute the percent error for each of the months, but what we really want to compute is the total percent error for all of the months combined. To do this, we add together all of the percent errors. When we do this, what we get is something called a chi-square statistic. And how do we go about computing the value of this statistic? We'll start by looking at our original data. Then we think about our null hypothesis with the percentages we'd expect to get for each month if the numbers were proportional to the length of the month. And when we multiply each of these by the total number of participants, we get the expected number of birthdays in each month. Then we'll use the formula for percent error to compute the percent error for each month. And finally, we'll add up each of these percent errors to get 5.41. So what does this 5.41 mean? It's a measure of the difference between what you observed and what the null hypothesis would predict. This is the chi-square test statistic. Now, what do we do with this number? Like other statistics, we need to compare it to a sampling distribution generated by a null model. We'll talk about these sampling distributions in detail in a future video, but for now, here is a chi-square sampling distribution for this particular scenario, which has something called 11 degrees of freedom. Now, if our null hypothesis was true, then the number of actual and expected birthdays would be the same, so the chi-square statistic would be 0. So we'll look at the probability of getting our observed statistic, or another statistic further from 0, and this probability, the p-value in this case, is 91%. So this statistic is not strong evidence against the null hypothesis, and we can't conclude that some birth months are more common than others. In this video, we looked at a new type of scenario that used something called a chi-square distribution. There are several slightly different versions of chi-square, and the particular example we looked at was called goodness of fit. This deals with scenarios where there is one population with one categorical variable, where the variable can have more than 2 categories. And to use this, you need to report your data in counts rather than percentages. We computed a new test statistic that measures the difference between the observed and expected values, and then compared this statistic to a sampling distribution to get a p-value. In upcoming videos, we'll look at other versions of chi-square and look at the chi-square distribution itself.